Okay, here's our project. We were tasked with finding the volume of an irregular shaped object. Now, in this case, my object was this vase right here. I was given calipers, and we were to take measurements of the device of this object and use it with Mathematica to calculate or determine what the exact volume is here. In order to know what the volume is of any type of symmetrical object, we need to use or know the formula for calculating that. And in this case, it's the pi integrated from a to b the radius squared of that object, which is the same thing as saying pi from a to b, which is our initial to ending point along the x-axis of a function of x squared, or y squared, or again r squared. Now what I did is I took the bottle that I have. This is the general shape of the bottle, and I placed it along the x and y axis here, to where I use the x-axis to cut this in half. All I'm really concerned with is this part underneath this curve along the way. That's what my focus is on, is this area underneath this curve. So in taking the measurements of this, my highest point was roughly about 1.79 inches in width of the object. And remember, when I initially took the measurement, it was the full bottle, so it was roughly about just over 3.5 inches in width here at this area, at this point. But I only need half of that for calculation purposes. Now the length is 11.475 inches, and I did take approximately 37 equal measurements along the way, from the base to the top of the bottle. Each one of these was roughly about 0.31 inches apart from the previous measurement. Now all I've done is I've taken the values from A to B, and I've listed them here in the same formula we looked at just a moment ago. I have my pi integrated from 0 to 11.475 of f of x squared, which is the function squared. Now in this situation, I'm not given a function. I had to take the measurements of these to determine exactly the general shape of my object. Now I don't have any type of f of x to finish my calculation at this point. There are several ways you can do it mathematically, using Simpson's rule, and blending that formula with the integration formula of a circle here. But luckily for us, we have Mathematica, which makes our lives infinitely easier, as long as you understand what to do here. Now what I did is this looks like a lot is going on here, but all that's really happening is I'm listing my points. All of these just represent individual points along the way. This column is exactly, this information is displayed in this matrix here. This column is all my x points. This is, like I said earlier, approximately 0.31 inches apart from each successive point. These are my y points. These were my original measurements that I took and wrote down when I initially started, and these are my y measurements cut in half. That's all these are. And this is what I really needed, not this so much. This is exactly what I needed, because this is my radius of the bottle. So list plot, this right here basically just lists each of my plot points. That's all it's doing along the way. It's taking from my first column and my third column and listing them along this this graph here. Now this interpolation command or function, this really is what kind of gives us our f of x. This interpolation tells Mathematica to estimate um, approximate functions from one point to the next. And in this situation, the next graphic I'm going to show is basically just the two graphics superimposed on each other. We have our list plot and our f of x estimates along the way. Each one of these is an estimated f of x from one point to the next, summed up to make this entire smooth or relatively smooth curve along the way. Now the parametric 3D command here, this takes that f of x and creates a 3D graphic or visual of this shape right here, and along from 0 to 11.275. And if you look at this here, this is the actual shape of my bottle. Let's see here. There we go. And you can look at it any which way. Adjust this here a little bit. That's centered. Okay, and there's this is pretty much what all the hard work was for, was to get to this point here. Able to look at a three-dimensional form of my bottle, simply done with just the measurements that I took from it, and that was it. This next part, this next command, the integrate command, is the same thing that I showed earlier. It's this function, but now I have an f of x. Earlier I had no f of x, so I couldn't finish the calculation. Now I have an f of x which is defined within Mathematica using the smaller estimates of f of x along the way. So now I do have an f of x. Now it doesn't tell me what f of x is, but Mathematica knows what it is, and it's using that f of x. If you notice here, here's f of x. It's using to calculate this area, or this shape right here, to determine the shape. Now using that command, pi times integral of f of x squared from a to b gives us approximately 46.636 cubic inches, and that is the volume of my